We're going to go ahead and take this up a step. So we're going to have multiple rates going on. Don't freak out. I think sometimes what happens in these though is we do have some product rule going on. And we'll take a look at this. So the height of a rectangle is increasing at a rate of 11 centimeters per hour, while the width of the rectangle is decreasing at a rate of 9 centimeters per hour. So I'm just going to draw a quick little picture of this. So this time it's a rectangle, not a square. And so basically the height is increasing. So it's going up. And I'm not sure exactly how we would draw that or picture that, but you could see like, something like this. Maybe the height is increasing. So dH dt, the derivative of the height is increasing at 11 centimeters per hour. And then the width is decreasing, so that's kind of coming in, right? And so that means that our dw dt is 9. Is it positive 9 or negative 9? Now it's decreasing, so decreasing means negative. So it's actually going to be negative 9. The rate of change is negative. Then at a certain instant, the height is 3, and the width is 8. Okay, so what is the rate of change of the area of the rectangle at that instant? So area of a rectangle is length times width, right? So if we want to find dA dt, we're going to have to do the product rule. So we're going to do the derivative of L times W plus L times the derivative of W. Just product rule, F times G plus F times G prime. Plug in what we know, which we know everything here, right? It's just got to be careful the way we plug this in. So we're going to put, for dL dt, oops, why did I use length times width? We're using height and width, right? So instead of L, let's call this width times height. Same formula, it's just multiplying. If this is W, this is H. Now that makes a little more sense. So we're going to have negative 9 times 3 plus 8 times 11. And that's going to be negative 27 plus 88. Which is 61. And that's it. Let's look at another one. So this one's a cylinder. We have a cylinder. We also have a pyramid. They give us the formula here. Kind of nice of them. Same thing with the cylinder. So the radius of the base of a cylinder. So if you don't know what a cylinder looks like, you got that kind of like circle on the bottom, if I can even draw it. That same circle on the top. And then, maybe it'd help if I just drew lines. Not a perfect cylinder, but the radius of the base. So we have this base radius, and it's decreasing. So dr dt, the change in our radius, is going down by 9. And then the height of the radius, so this is the height, so dh dt, is increasing by 2. Then at a certain instant, the radius is 8, and the height is 3. Sometimes they're going to leave one of these unknown, and we're going to have to go to this formula to solve for it. Just a heads up, but I think that's one of the future assignments. So what is the rate of change of the surface area, I meant to drag this up there, of the cylinder at that instant? So surface area of a cylinder was given to us down here, 2 pi RH plus 2 pi R squared. So when we want to find this derivative, d dt of surface area, we're going to have to do the product rule on this. So it's going to be 2 pi times dr dt times h plus r times dh dt. Then plus 4 pi r times dr dt. So just took a little product rule there. That's the most difficult part. Then don't forget your chain rule on that. Now we just substitute everything that we know. So it becomes 2 pi times dr dt is going to be negative 9 times h is 3 plus, we're keeping this in terms of pi, so that's going to be 8 times 2 plus 4 pi times 8 times negative 9. 2 pi times negative 27 plus 16 plus 4 pi. 4 times 8 times, we'll do that a little bit. 4 pi times negative 72. Almost done. So we're going to have negative 27 plus 16 is negative 11. So this is going to be negative 22 pi. And 72 times 4. Negative 288. So 288 plus 22, 310. Let's hope it's there. And it's a negative rate, so that means we're just decreasing at that moment, right? So the surface area is going down, which makes sense because our radius, which is being squared, it has a much bigger effect on the problem isn't decreasing. So if we're decreasing the radius and it's decreasing by a larger number than the height's increasing. So overall it makes sense that this would be decreasing if you think about that problem. But that's the idea. Same thing for this pyramid. You're basically going to go through, use this formula. You do have a product rule to apply to it. And I'll leave a detailed solution in the notes on that one.